So we're going to start with pumpkin stoichiometry. It's got nothing to do with pumpkin. We're just pumpkin's the container where the stoichiometry occurs in. And so the fireball is due to acetylene gas reacting with oxygen in a right stoichiometric ratio to get, I always say, good cake. In this case, a good explosion. I want all the acetylene to react with the available oxygen. Okay, and you can see the fireball that resulted inside the pumpkin in these reactions that I would normally do outside, but I'm not going to do because of raining and for COVID reasons. But this fireball is about 3,000 degrees centigrade. Okay, pretty hot. And if you're going to make gases, combustion makes CO2 and water vapor. Okay, CO2 and water vapor expanding with that tremendous amount of heat creates the explosion. Okay, the sound of an explosion is due to the air rushing back to the vacuum. So we're going to give off tremendous amount of heat, produce gases in the chemical reaction. Those gases expand outward, and they push out the chemicals. You've got a vacuum of space here where the air rushes in, and that's the explosion. But in any case, let's talk about the reaction because it's everything that we've been doing so far. All right. So here is the chemicals involved. I'm going to take, and I can't have acetylene. Okay, not allowed to have acetylene tank, so I make it. Okay, interesting. Downstairs in shop, they actually have an acetylene tank next to an oxygen tank, and they use it as a torch. So they can have it in shop. I can't have it. Kind of weird. All right. Any case, so I take calcium carbide. It's a salt. It's made of calcium plus 2 ions, and it's made of this polyatomic ion of 2 carbons triple bonded to each other. We'll learn that's 3 pairs of electrons and a negative charge on both. So this is a C2 negative. So if I was to draw this, okay, it would look like something like this. It's really what? C2 negative 2, okay, polyatomic ion. Any case, to make the acetylene gas, I basically take my pumpkin, hollow it out, take the top off, have a plastic cup of water, and I drop water onto the calcium carbide. And it fizzes, and it makes a gas. And why does it work? Well, this is a crystal of calcium, and then C2, I'm sorry, here's the C2, negative 2 right here. So here's the calcium carbide crystal. Okay, so this is a polyatomic ion, and the calcium, if you notice, is in between that ion for stability. So this calcium plus 2 attracts a negative 2 ion. It's a salt. It's an ionic crystal. Okay, it's one of these. Okay, it's got a little different arrangement because it's bigger, but it's a 1-to-1 arrangement. So this is a salt. And I'm going to drop water. And what's going to happen is I make this. Well, here's what happens. It's so very interesting. I love the chemistry here. Okay, we know oxygen is smaller than H, right? It's over here. So oxygen pulls in electrons. And we learn in AP Bio that these are electron deficient H's, right? We call the word electronegativity. We pull in the oxygen. So these guys are kind of missing their proton. Now, what is a hydrogen atom? If you go on the periodic table, it's got a mass of 1, and it's got an atomic number of 1. You should know from this summer, that means it's 1 proton and also 1 electron. So when you draw this, here's the proton. By the way, the mass of a proton is 1. There's no neutrons. And here's my electron, and sometimes I'll draw it in an orbit. It doesn't move in circles, but we'll just draw it like that. Okay, well, if its electron is pulled away from it, like in water, essentially what's dangling out here are protons. And so there is something very negative. Well, we would say that this H moves here. Okay? And so that creates a bond. And another water molecule's H is attracted to that negative and moves there. Are we transferring electrons? No. We know these electron deficient H's are attracted to this negative end of the carbon, and so a hydrogen is transferred, not an electron. So therefore it's not a redox reaction. We're not transferring electrons. This has 8 electrons. And once this water molecule, okay, gives off a proton, which is just a hydrogen without an electron, right? It's just a proton with electron. So once it just gives up its proton, and by the way, it's positive, these 2 positives of 2 waters make this a neutral compound. And the result of the water missing an H without a positive is this what? There's still 8 electrons minus 1 positive that moved over, which is the proton. This is a polyatomic ion. And so 2 hydroxides are made. That's where that comes from. So when you think about it, when we drop the water, okay, what's going to happen is the it's not going to be the water attracting and pulling the ions away. It's not dissolving in this case. The H's from the water react with the carbon. Those protons come on, 2 pluses come on to these 2 negatives, and this thing becomes neutral. If it's neutral here in the salt, calcium plus 2 doesn't attract it anymore, and calcium comes out. And of course, we're producing what? OH minuses. So the calcium that comes out of the salt, because there's nothing attracting to it, can now what? Bond with the calcium hydroxide. And by the way, that's insoluble, and you make a new crystal. That's a white compound. By the way, that's called lime. All right? So let's look at the reaction. Hopefully everything stays together this time. Okay, and that's, of course, our stoichiometry, but we're going to go the other way. So we're going to make oxygen. I have to have enough oxygen because we're going to combust acetylene here. All right? And this is the reaction. I'm going to take hydrogen peroxide, decompose it. This is called a catalyst. It's not part of the reaction. And I make my oxygen. So I take my pumpkin, hollow it out. In a flask, I have hydrogen peroxide. I drop a catalyst, and I bubble out water vapor and mostly O2. I want to make sure all the O2, there's more than enough O2 to react with the acetylene gas. And here is the reaction that we're trying to do. This is combustion. It's a hydrocarbon that I made from dropping calcium carbide in water. This is what I made by the hydrogen peroxide. And we got to balance to get an idea of our what? Ratios. Okay? And when you get this weird 5/2 business, because, hey, 2 carbons, so I throw a 2 here. This gives me 4 oxygens plus 1, 5 oxygens. So I have a 2 here, tough to get 5 when this has to be an even number. So if I times it by 2.5 times 2, it gives me 5. Now, can you have 2.5 O2s? No, but sometimes you'll see it written that way. So if you multiply by 2, okay, we get a 2 to 5 ratio. So if you think about that, I've got a lot of O2 that I need compared to the acetylene. If not, I'm going to have the limiting reagent in my reaction be what? If I don't have enough oxygen, that'll be limiting, and I'll have some of this not reacted. That won't be good cake. I want to make sure I've got enough oxygen to make all of that go in that small space. So we do the reaction, and boom, it happens, and that's a still frame. Just so you know, acetylene is used for welding. Okay, and look at the same color. And it can get as high as 3,500 degrees Celsius. That's going to expand the gases and create the explosion. All right, and also in the past, we've had acetylene torches or acetylene lamps. What they do is take calcium carbide, and in some water mixture, they bubble the gas out, and there's an open flame. They used to wear these as mining helmets, okay? But that really wasn't a good idea, because if you're mining things like coal, and you've got coal dust, it's explosive. Just like carbon dust and flour dust is explosive. Dust with carbon has high surface area, rate of reaction so fast. It's called grain elevator explosion. So in any case, they used to have these acetylene torches. And back the olden days, before they had regular running lights for cars, they had acetylene lamps, okay, for the cars to see at night. Okay, good times. All right, so let's get to the reaction to see it. And I'm going to see my cursor. All right, you ready? Okay. So now, hold on. Before we do this, and again, I normally would do this outside, but for reasons I can't do now, I'm going to start the reaction with this sparker. I have basically a barbecue sparker attached to a stereo wire. Okay, for those at home, I don't know if you can see, but there's a spark over this way. There it is. Sometimes you can see it at home because it's the frames. There we go. Okay, so you guys can see that spark. And that, by the way, what creates the spark? Pressing down on a piezoelectric crystal. Can't get away from the science. In any case, that's what this wire is here. And when I go 10, I'm going to hit that. That little spark is the activation energy to react the oxygen with the acetylene. So let's do it. Stop talking about it. 9, 8, 7, 6, 5, 4, 3, 2, 1. See the Now that's loud. For outside, that's a loud explosion. Because outside you have nothing of, you don't have the rebound effect. If I was to do that in here, you would, it'd be, I mean, it might hurt your ears if you didn't cover them. And we would shake the foundation here and people would run in and be mad. But I want you to watch it one more time because it was fun to do. Do that, replay it again. The phys ed had a class, so they came over, so the pressure was on. I probably should have told them to watch her.
6, 5, 4, 3, 2, 1.
It hits her phone. She's saying ah. All right. Again.
That was a good ratio.
Why was that a good ratio? Because I was pretty explosive. So let's play it in slow-mo. Okay, so watch. And that piece is going to get her right there. Boink! On the phone! All right. And that was pretty good cake right there. All right. And look at this guy. He's still looking at a piece that went in the air. You know what he's looking at? The top. And all you do is take a pumpkin out. Okay, it looks very dangerous, but you put it like on an old metal crate, or if you got an outside fire pit or something, and take a toilet paper and you douse it in kerosene, and basically got a wick. You know, obviously you don't stand by it, but it looks pretty sick when it's on your lawn burning. It'll go for about an hour. It'll wait for an hour. All right. But in any case, happy Halloween. Let's go to the explanation to. Okay, so we have a food critic that was sitting in North Riverhead restaurant, and it was a French entree. It was a French toast. Okay, but I want to show you that as weird as this may have looked, for some of you guys struggled with this maybe. It's a better at 2 test. This is everything we've done before, right? So we're trying to figure out whether this is potassium chloride, sodium chloride, lithium chloride. Okay, that was the whole point of that. And so what we did is what? To figure out, now he had a problem, dangerous heart rhythm and muscle weakness. There's a reason for that, okay? The poisoning is under investigation, okay? Any case, but what did we do here? We had a white solid that we scraped off the French entree, French fries, okay? And we dissolved in 40 milliliters of water. 200 milliliters of a 0.1 molar solution of lead nitrate was used. Oh my gosh, we've got a volume, convert to liters. We got a molarity. We can get moles of our what? Excess compound. All right? And then, of course, we dissolved it into this solution. And a yellow precipitate occurred. Not sure where we might have seen this reaction before. Okay? And so we made a yellow precipitate. And this is a positive test for lead 2 chloride, which I'm telling you that's the precipitate. Okay? And you could look it up. All right? The precipitate was filtered, dried, and was determined to be 2.282 grams. Is the suspected poison just table salt, the common additive table salt NaI, or was it a more KCl or LaCl? So this is the identity of an unknown compound using precipitation analysis, aka gravimetric analysis. This is everything we've been doing. Okay? So this should not have been difficult, although I thought some people thought it was. Now, some people did this by just plowing through and seeing which one it was closest to. It's not what I wanted, but you should be able to write the formulas, okay, see who the net ion is, and do the following. So what did I do? They told me that was the dry precipitate. I convert to moles, knowing that it's lead 2 chloride. And what do I know? For every 1 lead 2 chloride, there's how many chloride ions? 2. It's about the chloride ions. Why? Because the salt has 1 chloride ion per formula. So I took the moles and I times it by 2. I got moles of chloride ions, 0.0168. What do I know? In my unknown metal chloride, it's a 1-to-1. So the moles of the chlorine are the moles of this. So I have the moles of my what? MCl. And so what I did was, just like your lab, I said molecular mass, fancy, is grams over the moles. From the precipitation analysis, we just plugged in the what? The the moles. And from scraping the white substance off the French fries, we've got our grams, just like our lab. And so what I got is 81.068. And when I look at the formula masses of these three, this one's over. Why? Because it's impossible to get all the what? Precipitate out. It's going to be an overvaluation because the moles are lower than expected, which drive this formula up, just like the lab. And now that I know it's KCl, I convert the grams using the KCl formula. I know that's limiting, I get moles, and I do my stoich. This is excess, and we're off and running. So as weird as it may have been for you, okay, it is everything we did. The only exception is I'm using a 2 to 1, not a 1 to 1 to 1 like the lab was. But we can handle that. That's what I was after. Okay? And moving on, this is important. You must be able to see what I'm doing here. So we noticed that the lead nitrate was the what? Excess chemical, as we did in the lab. The other chemicals got to be excess. Okay? And so here we go. Nitrates delivered the lead. The lead's locked up, except the lead nitrate was the what? Excess chemical. So a lot of the lead became the crystal, but you better show me one lead or two outside because it was the excess chemical. Who delivered the lead nitrate? The nitrates. There should be a lot of nitrates because there was 2 nitrates per lead, and it was the excess chemical. And none of the nitrates are here, so there should be more nitrates than anything else. Who is the limiting reagent? Well, the KCl, except the K plus is not in the crystal, so it's spectating also, but not as much as the nitrates. Why? Because it's 1K to 1Cl, but it's the limiting reagent, so less of it was used. And that's why I have nitrates bigger than K pluses, bigger than lead nitrates, than the sodium ions. Okay? If you like calculating the atomic mass, I did it that way as well. So, as foreign as you may have thought this was, it's everything we've been doing. And again, it's a process. So if you didn't do well on this, better out of 2 quizzes that you handed in. And it's only a quiz. All right? So I want to do one demonstration that relates to the pumpkin explosion. So I'm going to take some ice. So for those that are still with me, I got my ice. Maybe hear the term icy hot. Okay? So I'm going to add some water to my ice. Okay, here we go. So I've got water to my ice. There it is. And I'm going to take a can of, you can see why it's covered. They don't want moisture. This is calcium carbide. I'm going to drop it into the ice. What's going to happen? Just like the pumpkin experiment. What's going to happen? I'm going to make acetylene gas. Yes? Notice. Okay. So, think I'm not working hard at this? Okay. So I'm going to drop some calcium carbide into the ice water. But it's the water H's that are come off. You hear anything? So what is that, probably? Oh my God! The ice is on fire! The ice is on fire! If you look, what color is that ice?
It's not.
What's that? In fact, if you can see in the air, there's some soot in the air. For those that can't see at home, this ice now is black. Why is it black? What color, what element is black? Carbon. Soot. The other class I did it gave me more soot. Look at this. Look at this. Why is it so black? The ratio was bad. Good. You see black here, party people. I know it's hard to see, but I'll put it in the light. You see black here, or soot. It's because not all the acetylene had enough oxygen. This is not what I wanted. In the pumpkin, I wanted what? The limiting reagent to be the what? The acetylene gas? Yes, I wanted this. All the acetylene gas didn't react. is incomplete combustion here because there was not enough oxygen, all right? So, and the white solids you see in the bottom, that's the precipitate of calcium hydroxide. I love chemistry. Okay.